You'll probably remember that earlier in the semester, I gave you kind of an intro to ant colony behavior, because that's the system that is motivating some of the work that I'm doing. At least it's useful as a system of study, because you can observe it directly. And ants are really interesting. They're eusocial insects, which means that they must live in communities in order to survive. They also have no leader. There's no top-down guidance happening. Everything that ants do is based on local interactions that they have with their environment, and with other ants that they encounter. In my project, I'm focusing on two things with respect to ants, which is stigmergic information, a fancy way of saying information that's encoded in the environment as opposed to in the nervous system of the ant. So as ants are walking around, they can find, for example, pheromone trails that other ants are leaving as they're coming back to the colony after finding food. And that's the kind of information encoding that I've been interested in, to figure out how can that give rise to collective behavior. So I also introduced, so that was the ant stuff. And the particular framework that I'm using to model the ants is active inference. In order to understand active inference, there are a few key concepts we need to review. So I gave a few examples about perception as inference. And you have the shadow of Michael Jackson, which turns out to not really be Michael Jackson. So you have to, when you first saw that shadow, you came up with our intuition is to come up with some explanation for what is the actual cause generating that observation. And this idea of perception as inference is claiming that that is generally how we perceive things. Next, I briefly introduced last time the idea of a generative process and a generative model. A generative process is whatever is actually happening out there in the world, which we don't ever have direct access to or contact with. Rather, that generative process, which could be atoms in the world, for example, they generate observations, they generate sensorial data that we actually perceive or have access to. And we, in our minds, have some kind of generative model that is representing the state of the world. It's our best guess about what the world how it works. And we use those observations that come in to update our model of the world, or we can also take actions to change the kind of perceptions that we receive. So as we're working our way towards active inference, it's important to start off with Bayes' theorem, because that's the mathematical workhorse, mathematical tool that is giving us the rationality behind how do we update our beliefs given information that is coming in the most optimal way. So Bayes' theorem, just to review, tells you that if you have a hypothesis X, some explanation about what's happening X, and you have some observations, some data Y, the correct way to update that is given by this equation. So you have some prior over the hypotheses X and a likelihood model Y given X. Let me just show you this diagram, which I think is a bit more instructive. So let's consider an example of a world that only has two kinds of things: apples and frogs. And that there are only two kinds of observations that you can make about that world. Either you see something jumping or you see something not jumping. You also have so you start off with some prior belief about what's the probability that there are apples in general or frogs in general out there in the world. And then you have some likelihood model on the bottom that is your sense about if there is an apple, what's the probability that you see it jumping or not jumping? And the same thing for frogs. And you combine those two pieces of information using Bayes' theorem to generate a posterior belief over what is the probability that there are apples or frogs out there in the world. So now we're getting to the real meat of the matter. active inference, which was developed by the British neuroscientist Carl Friston. And there are two roads that we can take to understand active inference. And there's also a lot of math involved, which we're not going to go into in this presentation. Instead, we're going to focus on what is known as the low road to active inference, which, as you see in the bottom, starts off from Bayes' theorem as the motivating mathematical principle. On the top, you're seeing the free energy principle, which I'm not going to go into detail, but an important concept to, at least an interesting motivating concept in the free energy principle is this idea of a Markov blanket, which is formalizing mathematically our intuition about what does it mean for something to be a thing that is distinct from other things out there in the world, a thing that's distinct from its environment. And the idea is that what makes a thing distinct is its boundary. And then there's some math for how you can describe that boundary based on Bayesian networks. So with the low road, we had talked about perception as inference. Now I want to give you a sense for why the active part comes in the name. And for anyone who's interested in trying this out with me, I want to invite you to do a little demo and close your eyes for just a second. And if you can gently take your hand and put it on one of your legs. And if you think about what is, without moving that hand, try to get a sense for what's the texture of my leg. That's probably hard. But if you start to move your hand around a bit more, you get a better sense for what the texture of your leg is, depending on what you're wearing. And that's the intuition behind the key idea here. Active inference is telling us we have perception as inference. Now we can also, in parallel, think of action as inference, because in order to make sense of the world, we need not only to passively let things come into us, we also have to engage and we have to move, we have to act in order to collect more information that confirms our beliefs or updates them, or to influence the world such that it's more consistent with what we imagine it is. So just to tell you, oh, it seems I'm out of time. That one's, how much time do I have? Okay, so just to give you a short anecdote of how this happened for me. In 2021, I was in Cambridge and I didn't have anywhere to live for a while. So I met someone who told me, hey, if you come to my frat house, there's a storage room. You could stay there for a bit. So I did that, and I was sleeping on a table for a few months, which was fun in its own way. However, you can imagine in a place like that, there are plenty of rats, and I could hear them scurrying around all the time. One night, I woke up all of a sudden because I heard the scratching. And I was sure that the rats were coming to nibble off my ear. So I took out my phone, turned on the flashlight, and was looking around, shaking it. Where's that damn rat? It turns out, initially, I saw the shadow of something moving, and I was like, there it is. But as I started to flash the light more carefully and look more carefully, over time, that real perception that I have of there being a rat transformed into what it actually was, which was just the shadow of a fan that was in my room. So this was kind of like a visceral, vivid experience I had of this kind of action as inference idea. So that's the conceptual stuff behind what the work I've been doing. In the last few minutes that I have, I want to give you a sense of the tools that I'm using to try to work with this, which is introducing the work of Vikash Mansigha, who has developed the Gen programming language for doing probabilistic programming. And for the sake of time, I'm not going to go too much into detail of all of the of how it works, but it suffices to say that generative probabilistic programming is a way of representing these generative models that I was talking about as code, as a program, a generative program that runs same way that a Python script does, but that is making random choices along the way. And you can perform inference on these generative programs in a very computationally efficient way. So this is like, just to give a little example of what a generative program can do. If you want to infer from some depth input stream, the floor and ceiling in some video, you can do that, and that's what the code looks like. It's actually something that you can interpret, which is important if we want to design interpretable intelligent systems. So I'm just going to skip around a bit. The kind of generative program that I'm trying to write is known as a POMDP. Probably many of you are familiar with that structure. This is what my code looks like as an outline. Sorry, it's very dark, but it's a POMDP, the outline of a POMDP in Gen. And why is this important for what I'm studying? It's because it's important for us as scientists to be able to get a good sense of what, for example, an ant is doing in its mind. But this is to be done in an interpretable way and in an automatic way, because we can't always write down generative models manually. And it has to be scalable if we want to study collective systems, which by definition involve many, many agents.